Hello, good morning, everybody. We are on July the 2nd, and welcome to this workshop about Watson computer vision. I would like to thank Philippe Grégoire and Jean-Luc Collet, who helped me assembling this material, the material we'll present today. The agenda for today is the following. So we will deliver an overview of what computer vision is and how important it may be for your businesses. And then I will go on to present the Watson visual recognition tool. After that, we will use Watson visual recognition in various ways, first with the API, then with Watson Studio and the user interface that is provided within Watson Studio. Finally, we'll deploy custom models on Android, and I will tell you about how to do that on iOS. Next week, on July the 10th, Philippe Grégoire will tell you about more advanced items about the IBM offerings on computer vision based upon Watson OpenScale, IBM Adversarial Robustness Toolbox, etc. What's computer vision? So the basic idea is that computer vision enables computers to analyze, process, classify, understand, label, and caption digital images. We use that capability in many places, for example, to analyze sports tournaments or to analyze pictures in order to understand what are the elements, what are the objects that are present in these pictures. Sometimes it may be very difficult, like in the one with the woman with the giraffe. So who is there? Is it a woman? Is it a special woman who has a giraffe head? So that's something of a challenge, even for human, but even more for computer vision models. Computer vision is a big market and it is growing exponentially. So we are in a society which is going digital, and many elements are going digital, including images. And of course, the images are really easy to produce now, thanks to smartphones, thanks to other elements, digital cameras. So it's a very growing market, very large market nowadays, and video represents 80% of the global internet traffic. So from this environment, there are lots of elements that can be analyzed. So what is in the picture? Is my brand mentioned there? What is the feeling of the customers using my product, etc. So there are lots of elements that can be very useful and that will rely on computer vision. There are different flavors for computer vision. Image recognition, so find images shared online. You can look for specific objects or brand logos, for example. You can do some image analysis, so to identify what's within an image, or you can do video understanding. Video understanding, in fact, is more like in analyzing still images, but that are recurring, and you can from that understand the movement that is occurring within a video. There are various flavors for computer vision. So computer vision is a wide embracing term. So you have got image recognition. So you find images, in images you can find specific objects. So it's very useful to recognize that there is a car, or there is a tree, or there is a plant, or for example, what kind of plant is it? So there is for example, an application that can help you become a botanist in a very easy way. You just take a picture of a plant and you get the name of the plant, which is sometimes very difficult even for a good botanist. So image recognition helps you recognize and analyze what's in an image based upon the model, and we'll see what it means for the tool Watson visual recognition. You can then go a bit further and analyze the image. So of course, you understand that there are elements within the image, and now you want to connect some kinds of relations. So you can understand whether there is the name of advertisement or of a trademark of a brand that has been going to advertise in a specific program, for example. So is the brand present X number of seconds, which is the contract, or is it not present for that amount of time, etc. And there are as well the features or use cases for video understanding. So understanding the motion and analyzing the motion within a video. So at the very starting point, it can be analyzing that a person or an animal is moving within the video. It can be used as well for understanding the scenery around the car, an automated car, for example. Computer vision matters in many places, so matters everywhere is a bit difficult to argue, but it's present in many places. So it's understandable that you can, with Zoom or with WebEx or with Teams, etc., have communications and have the ability to communicate through the tool. So sometimes, and for some features, you can analyze the face with the agreement of the persons, of course, and understand the emotions of that person. So it can help understanding better, even if you are not face to face, what are the corresponding or the person you are talking to is feeling. Or you can as well think of it in the cars, in the autopilot. So you need to see, or the car needs to have a good understanding of its surroundings. And that's something that can be provided not only by radars, but as well by a kind of vision capability provided to the computer driving the car. It can be used as well for surgery. So there is on the right-hand side surgery mechanism doing some very specific surgery based upon, of course, recognition of what the tool is acting upon. And to recognize what's going on, you need to have some kind of vision mechanism. You can as well in sports, so the replays, who's playing, what are they doing, or what they're organizing. And you see here on the left-hand side the blue squares around the enterprises that are mentioned in the picture, so that to validate that the advertisement is well done. I mentioned the PlantNet identification, so you can do that for recognizing the name, but you can as well do that for recognizing whether the plants are enough water or not. So it can be used for food, for example, for agri-food, the agri-food industry. So being able to identify that some fields are well covered, well receive enough water or don't receive enough water. And another kind of mechanism, which is a bit more funny, I would say, or the robots that have been created in the world have some kind of computer vision in order to recognize and to analyze the people they are talking to. In terms of use cases, if we take the various business domains, so there are lots of use cases. So if we start with the most difficult of them, and I already mentioned face recognition, is something that we tend now to avoid. However, there are lots of other things that can be done with video and computer vision. So public security and safety for smart cities, for example. So all the TV shows about spies and policing and experts, etc., are full of computer vision images. It's good as well for transportation planning and optimization. It's good for defense, etc. If we go to healthcare, so it helps what has been very much very much used during the pandemic, the telemedicine. So you can get an idea of what's the issue with the patient. The doctor can get an idea of what the patient fares thanks to the vision and thanks to the images you can store. You can think of the ability to analyze scans, MRI scans, for example. So in order to analyze some injuries in the brain, for example, or other kinds of elements. So creating a kind of ability to recognize things that are based upon models, based upon experience. In finance, so satellite imagery analysis for investment strategies. So that one I will be dubious about it, but well, that could be something interesting in case you want to have a global picture of a country. How does it fare? Is there enough wheat or enough rice going to be harvested this year. Emotional analysis, automating document extraction, security, education. So you can think of personalized education, student engagement detection by analyzing the behavior of the students behind their computer. I talked about agriculture for satellite crop field analysis, disease image recognition for fields, not for humans at that time. Science. So there are lots of elements in science that are using visual recognition, and some kinds of images that are created by computers are analysis of elements, for example, like the data that comes back from the stars, coming back from probes that are sent in the outer space. In energy, strategic or drilling, maintenance. Maintenance is something that can be done in any kind of industry. So for pylons, for railways. So for example, in the railways industry, there are some elements like the carriages. So they've got wheels. Those wheels may got rusted or may got in bad shape, and we have implemented with visual recognition a kind of a use case where you can there are images taken of those wheels. They are analyzed based upon analyzed with a model saying the wheels are okay or not okay, and if they are not okay, the train is stopped for some kilometers after that analysis in order to do the repair or to avoid the convoy to go too fast. So it's something that you can use in many places and for many usages, and it's something very, very interesting. It's something that has a relatively long history. So it started, and we're reminded of Marvin Minsky, who got the Turing Award in 1969 about computer vision. Another Turing Award, Yann LeCun, was made famous for using deep learning in this field. And another person, Ian Goodfellow, was made famous because of the generative adversarial network's ability to create and modify some images through some from deep learning algorithms. But one of the most important things that occurred in the computer vision environment was the creation of a database of manually tagged images named ImageNet. So ImageNet was a big endeavor where in order to be able to start training computers about what is present in a photo, 14 million pictures were tagged. So this is a cat, this is a lion, this is a car, etc. So 14 million images were tagged in a big database, and this database was the beginning of all the other breakthroughs, because in order to create a good computer vision tool, you really need to have lots of data, and trained data and tagged data is something that at the beginning was a big effort, big endeavor. Computer vision rely on artificial intelligence, so it's a branch, I would say it's a branch of artificial intelligence. And we see here the various eggs which are overlaid one against one the other of the different names and different elements regarding computer vision. Artificial intelligence. So artificial intelligence is a general name, and it has been around since a lot of days. So 1950, but even before, you can think of artificial intelligence in some way, even before that. The first games using computers simulating human intelligence, Menace, for example, was created in 1960. Deep Blue in 1997. Jeopardy 2011. Project Debater is more Jeopardy and Project Debater are more about understanding text, understanding voice. But of course, it's interesting when you are dealing and discussing with somebody to allow the computer to understand images as well. Because if you say, this is the proof of what I say, and you show a picture, if the computer has no eyes, that will limit definitely the capabilities of the computer. The machine learning capabilities in the 80s to 2010 have enabled the computer vision to progress very much. And the deep learning and reinforcement learning that have been made available since 2010 have really made a big difference in the capacities and the strengths of the algorithm of the models that have been created since then. So you will see in those elements, so artificial neurons and all the elements that are mentioned, so artificial neural network, convoluted neural network, recurring neural networks, generated artificial adversarial networks, etc. So there are lots of acronyms that are used in this environment, and that relates to algorithms that have improved the capabilities to recognize things, objects within a picture or a video. And of course, everything depends on big data. And I mentioned the ImageNet capabilities that was made available in the beginning of the years 2000. So where is IBM? What is IBM doing in this environment? And how do these products fit within the global IBM portfolio? The IBM portfolio is mostly based on cloud nowadays. So everything that we deploy, we provide, or most of the things we provide are in some way related to cloud, and they can be exploited. They can be run on many clouds. That's the Watson Anywhere or the IBM Cloud Pak environment, which enables software to run not only on IBM Cloud, but as well on premises or on other clouds. However, the only element that runs only on the IBM Cloud is Watson Visual Recognition, so which is a service built upon open source frameworks, and which it will be accessed, and we'll show that through Watson Studio. So it will be a service that you can access through APIs, and that currently exists only on the IBM cloud. So there is no way for the moment to have it on a machine or on a private cloud. If you want some equivalent capabilities and even more specific capabilities, you will go on the left-hand side with IBM Visual Insights and IBM Visual Inspector, which were born from the Power AI environment, Power Artificial Intelligence Vision, Power Artificial Intelligence capabilities. So these are elements that you can install on site and of course run in the cloud if you like, but you can as well install them on your own machines, and they will provide the same or even extended capabilities. For example, if you want to analyze how a production line is faring with yogurts coming every millisecond, you need something that is very efficient in terms of network. And even if the network is very good with IBM Visual Recognition, the IBM Cloud, it's not fast enough for analyzing things in a very short time. So Visual Insights will help with that, as well with the Visual Inspector. So the Visual Inspector will be the ability to provide models and to install those models on either Android phones or iPhones, and to do the analysis without even any connection to a server. So, for example, for maintenance personnel, when they go on site, when they go and see whether a piece of a plane is rusted or not rusted, or rusted enough to be repaired or not rusted enough to need a repair, they will use the Visual Inspector tool, which is a model deployed on a mobile device. And that's something that we can as well provide with a visual recognition service. We'll see that in the last tutorials of the morning. What differentiates the Watson Visual Recognition from the other tools and all the other tools that you can create in Watson Studio with all kinds of frameworks, Python, Keras, Caffe, NeoNets, etc., is that visual recognition will provide you existing models, so you won't have to bother with creating from scratch models. You will be able, however, to customize or to create your own versions or your own adaptation of those models, and we'll do that as well. But the base models or the base work has been done before, and by some kind of translation of the capabilities of the base models, you will be able to have to adapt those models to your specific conditions. Up to a certain point, if you go further, if you want to get deeper into specificities of a model, you will need to go and to create your own models, and that's to be the topic of next week through Python and other tools. And in the open source frameworks, as mentioned, the adversarial robustness toolbox, in order to understand how the tools that are used for good can be used as well for bad, and how to understand and to understand how some of the elements that can modify some pixels and change the results of the models can be thought or can be understood so that this does not happen. So we understand that Watson Studio is a key element to build this environment. So if you need to go further than what Watson Visual Recognition offers, you will need to get into real data science. And to use real data science, you will need a lot of algorithms, a lot of tools. That Watson Studio will offer a user interface for visual recognition. So that will be what we are going to use today as well. But it will offer the capability as well to create Python notebooks or to create other programs in whatever form you want to make them happen in order to analyze things and to create and to exploit the open source frameworks that are, let's say, I wouldn't say fashionable, but they are very much used in this environment. So on top of a cloud environment, and IBM Cloud means either the cloud itself or on-prem with the capabilities of the cloud packs or on other clouds, you will have a scalable infrastructure as well as machine learning runtimes, deep learning runtimes, TensorFlow, Caffe, Keras, etc. And on top of that, some authoring tools that will be specific to the IBM environment with the neural network modelers, the streams designer, the APIs, etc., that are specific to the Watson Studio environment. The big data, Cloudera, Hortonworks, so the ability to exploit lots of images, for example. And now let's come to the Watson service for computer vision, the visual recognition service. Visual recognition is a service that can be accessed through the IBM Cloud Catalog, and you can access it and use it with the APIs. If you combine it with Watson Studio, you'll get user interface, a visual graphical user interface that will make it more easy to use the tool. And then this user interface is presented here. So you will have the ability to use either custom models or pre-built models. So the pre-built models are there are 3 now. So because we have taken off the face model, as I mentioned before. So we now have the general model, which can describe or which can identify things within images. We have another model which is dedicated to recognizing food, so identify meals, food items, dishes with enhanced accuracy. So of course you can recognize food in the general model, but the food model is more accurate for food. And there is another model which is explicit, so assess whether an image contains objectionable or adult content that may be unsuitable for general audiences. So we'll have a smart exercise with some pictures of classical statues, for example, just to see what happens when a nude or a picture that can be called explicit is presented to the tool. So these are ready to exploit, ready to use models. And for example, you can see here on the left-hand side how it's presented into the Watson Studio user interface. You see that there is a picture and there are all the classes that have been recognized with a score. So here the color is of importance, the fact that there are people, there are persons, sports, clubbing, blue collar, nightclub, building. So there are a certain number of elements that can characterize the picture based upon the general model. You will see that you can have an overview of this environment. You can test the pictures, so you can submit pictures to this model. And implementation, we'll see that later, will provide you with the snippets of code to embed this analysis into a program. For the custom models, we'll have two kind of custom models. One is about classification, and it will be used with the API version 3, and the other one is to detect objects, and that will be the API version 4. So version 3, version 4 are not, version 4 is not replacing version 3, it's just a different way to analyze images. Classifying will allow you to recognize tags or to associate tags to the image, whether detect objects, so object detection will provide the ability to not only detect objects, but to count them and to locate them within an image. So it will provide more information into the understanding of the image. But as you see here, you have pre-built classifiers, general, food, explicit, and the custom classifier, but there are no general detection models, so only custom object detection models are available. In order to see how it looks like, just a short demonstration. So I don't know whether I need to share my Firefox as well. So just a second. Okay, so do you see my Firefox presentation? Hello?
Yes, we see it.
Okay, so here is an example. Okay, so you see here a picture. So there are a certain number of pictures here. It's a presentation that is available on the internet, and you can use it whenever you like. You get here the analysis based upon the classes that have been recognized. So it's a jacket, it's a fabric, gray color, etc., tweed, etc. And you get as well the JSON, which explains what is returned back from the service and that you need to exploit with your own program in order to use it. So you see that there are a certain number of classes that are being presented. You see the score, and you see the hierarchy type that has been recognized. So here it was a jacket. Here it's another picture about a cardboard electronic device. So you see here the color, the device, etc. So the sequencer. So if you are looking for analyzing whether a piece of machinery is correct, it could be used like this in order to understand whether it works or not. And then another here about analyzing kind of scientific tool in order to see what happens. So I'm going back to the PowerPoint. Okay. The localization, visual recognition tool is on the first two steps that are mentioned here. So there are 4 ways to obtain a deep learning model. You can use a pre-trained model and transfer. So that's the gray part of the transfer learning that you see here. That's the way visual recognition and another tool named natural language classifier, but for words, are used. So based upon a pre-trained model, through transfer learning, you can customize the model for your specific needs up to a point. If you want to go really deep into the customization, you need to create a model, a base model, and that you will do with Watson Studio, Jupyter Notebooks, and the open source Keras framework, for example. So you will have much more work. So of course you will be able to do more, but you will have to do more as well. And if you want to go even further, you will have other elements. So with the ability for automated networks, neural networks, with neural networks feature of Watson Studio. The idea is that a data scientist needs a lot of power with GPUs. So that was one of the elements that enabled as well the rise of computer vision. So the ability to really process quickly the images. And there is this, I will not comment too much on that, but one of data scientists creates 20 hours of NVIDIA Tesla V100. So a data scientist dealing with computer vision really need power to his job, his or her job. What can we do with, in more detail, with Watson visual recognition custom models? So up to what level can we customize the visual recognition models in order to fit with some real use cases? So some of the examples that have been presented and that have been used by partners and customers, for example, looking for specific structures in satellite images. So here we see tennis courts, but it could have been as well swimming pools. So, for example, swimming pools and tennis courts were used in different situations. For swimming pools, for example, one use case was to see whether the swimming pools were filled or empty during a drought in California. So the Californian government said, do not fill your swimming pools. And so there was some kind of ability for drone or satellites to validate that the swimming pools were not filled according to the request of the government. Or in Spain, it was to validate that people saying that they have no swimming pool in their property had no swimming pool in the property. So it's another way to check whether people were compliant with the taxes rules. Other elements that have been seen as well as use cases, being able to analyze through images pipes and seeing some cracks or no cracks in the pipe. So being able to recognize a crack in order to send a team to repair the pipes. A more complex environment was to say, okay, we are going to repair some pylons for electrical distribution to see whether they are okay or not. But it's easy to say, okay, it's rusted, we're going to repair it. But sometimes it's not rusted uniformly, so you need to take parts, to take images and to divide them into smaller parts to understand where it's rusted and where it's not rusted. And for example, here, there are elements that are not in iron, like those elements that are made of glass to isolate the iron part and the electric lines. So in order to do that, it's not just analyzing a single picture, it's really much more complex because you need to divide the picture into smaller pieces and analyze each picture and do some algorithms to validate that what you see in the picture has some meaning and that you need to send or not the repair team to the pilot. So the basic idea is that you get a picture, you see something and you act upon that, or you don't act upon that. but in the most advanced use cases, you have a picture, you divide it into multiple pieces, you do some pre-work, and to analyze many images, not just a single overview of the situation. So in order to analyze and in order to make those use cases possible, there are a certain number of steps that are needed. And to create custom classifiers, so for example, the rusted part of a pylon or a crack in a pipe, you need to follow a certain number of rules. So a custom classifier is a group of classes that are trained against each other. It means that you are looking for something specific, the crack, for example, in the pipe. So you will take a certain number of images of cracks, different ways they look like, as well as some images of a pipe that has no cracks, and you will train the system against that. So you will have input images in various classes, so not only the images of the cracks, but the other images. You will train the classifier, so you will send the images as source to the classifier, and there are several technical steps, I would say. So the first step is that the image will be expressed as RGB values for a set of pixels. So in fact, it's no longer an image, but it's an array, it's a matrix that describes what's in the pixels that are in the image. So the values are converted into highly dimensional representations of the features. So in order to understand the great elements of the image, and the features are mapped either positively or negatively to the classifier to create the classifier. So you get a trained model, and you get what we call a custom classifier that you can use in order to present some images to this classifier, and to have the classifier say, okay, I recognize this swimming pool, that there is a swimming pool in the picture with a score of 0.6, 0.4, 0.8. The process itself, and you will experiment it in the Watson Visual Recognition environment, is to create a group of classes, a group of positive examples. So let's say, for example, you want to analyze in pictures of fruits, apples, bananas, and pears. So there are three elements, three classes, three set of pictures that you want to use to create a fruits classifier. But you need as well, sometimes we say it's optional. In reality, I think it's very useful to have a negative example. So you present to the system what you want to look for, and you present as well elements that are not what you want to look for. So it just enables the system to understand better what you're looking for. So what we call the negative example. So if you are looking for apples, bananas, and pears, and you will present, for example, vegetables or even cars. It's just that the idea is that you can present these elements that are not the fruits that you want to recognize. You will need to do some grouping and to do some preparation for that. So you will organize your files into zip files. So you will organize either in option 1 a zip file of all the apple pictures, a zip file of all the banana pictures, a zip file of all the pear pictures, sorry. Or you can do different things. So one zip file for all images with folders within the zip file, or you can even have the category Apple divided into two zip files. So it's just a way. These are different ways to do that technically, but the main idea is that you need to regroup the classes that you want to create based upon what you're looking for in the pictures. And that's what we see in the next slide. In the next slide, we see that, for example, if you want to recognize apples, and you want to recognize apples in the marketplace. So that's the kind of picture on the right-hand side, the bottom right-hand side, where you see a bunch of apples in a basket. If you train here on apples being separated from the others, the training will be not efficient. There should be some kind of similarity between what the images you are going to provide to the system, you want to recognize, and the images that you are going to use for the training. If you are going to recognize apples in baskets, it would be most efficient to provide training images of apples in baskets, not apples isolated. It's machine learning, even if deep learning models that you're going to build, it's not really as intelligent as a human being, which would say, okay, well, it is one apple, this is a bunch of apples. So be aware that its intelligence, up to a certain point, it's overall trying to find patterns, to match patterns, and if you don't define the right patterns in the training set, you will get some bad results. So here, for example, if in the training set, this is not a single image, it's a set of images where you have all kind of tennis courts. So if you have all those images of tennis courts, and here you have got in the test set an image of a tennis court that looks like what you've used in the training set, that's a good training set. So training and testing sets, you may need to have some similarity in both sets. If not, you're going to have some inefficiencies in your system. And that's the most important sentence here in this line. Clients who closely control their image training processes observe greater than 98% accuracy. So you are creating a pattern, and of course that pattern needs to be rather close to the images that you want to analyze. Do you need to have very high quality pictures? Well, apparently not. So of course you need to have good light, exposure, angle, so many angles, focus, color, background. So you have to have the training set that is meaningful towards your aim. But the pictures should not be very, very large. So you don't need to have a very high quality picture. So there is a minimum size and a recommended size, 244 times 244. And there are limitations inside. So based upon the fact that if you have two large images, it would take ages to upload them. So it's no use to have very, very high definition images. So if in your collection, so for the positive classes, the negative class optional, but I would recommend it. The number of images that you need per class is 10 images, so that's a bare minimum, I would say, in order to do some transfer learning. You are going to use zip files, and the recommended amount of pictures per zip file is 150 to 200, so that's a kind of rule of thumb for creating those classes. You can provide up to 10,000 images, and there is a limitation of 100 megabytes per zip file. So that's the kind of information that you need to take into account when you are creating your training sets. In terms of image pre-processing, so I've talked about the fact that, for example, for the pylons, if you wanted to recognize rust on it, you would need to divide the pylons into smaller pieces. There is the subject matter of the classifier. So if you want to recognize this, okay, is it a button or is it a chimney? It looks like a chimney on the roof. It should at least take 1/3 of the picture. So it should not be a small detail in a picture. If you want the pattern to be efficiently recognized, it needs to get at least 1/3 of the picture. So if you don't have a picture where it's used as 1/3 of a picture, you may need to enlarge it or to refocus it in order to get that information. So you can either tile, if that doesn't work very well here because the chimney is separated into many pieces, but you can tile, you can zoom, you can crop, you can resize, you can scale in order to get good training images that are that bear some similarity to what you're going to analyze in the future. So then, okay. So one classifier, so we saw the ideas of bananas, pears already. So some elements that are needed to go further. So one classifier is one model. So positive from other classes are trained as negative. So it means that you can use other classes. If you're creating a fruit model, you can use dogs as negative classes, for example. Here, cheese as negative classes. You can retrain the model, so you can add more classes, for example. In the fruits, for example, here you can have, we had apples, bananas, and pears, and you can add oranges in order to create or to complement the model with a new class. So you can update your models by adding new sets of positive images to existing classes. So you can add more apples, for example, if you think that the apples are not well recognized, or at least the apples are not, you want to recognize apples in different environments. And you can split class, so red apples and green apples, for example, but you should do that with caution. And if you want to do that, you better start from scratch rather than trying to tweak an existing model. So here, training and retraining, so it was not apples, but it was green pears and yellow pears. So you can create, the idea is to create a new set of categories. So not only be able to say, okay, it's a pear, but within the pears, being able to identify the green pears from the yellow pears. So just as an element, you can add more negative examples taken from other models that are unrelated to the fruits models that you're creating. You can add new class, orange, for example, here. You can have new examples to an existing class, here apples, or you can even complement an existing class with subclasses like green pears and yellow pears. If we get a bit more into the classifier, so we have seen that we have got that score that comes back from the system, from the processing. So score is the response to the classification. So it defines the true or false or positive or negative conditions of an image against the class. So it gives you whether there is some resemblance or some similarity between what is in this image and the apple or orange or pear class. It's important to understand that those classification, it's like sorting letters with a certain number of boxes. So if you've got a letter to sort and you need to sort it, you will put the letter in one box. And it's the same thing for the classifier here. So even if you present a car to a fruits classifier, it will say that there is some pear in it or some orange in it, which may sound ridiculous, but it's a classifier. So the role of the classifier is to classify, and there is no way for it to say, okay, I abstain and I don't answer. It will answer that there is limited resemblance, limited similarity between a car and an orange, but there is maybe 2% or 3% similarity between the training images and the image of the car you're submitting to the classifier. So just to clarify this point. So the classify method, so that's the API version 3 method, produces a score between 0 and 1 for each image for each class. So it's not, it looks like a pear, and it's definitely a pear, not an orange. It will have some similarity as well for bananas and for pears and for apples. Custom classifiers use binary one versus the rest models to train each class against the other classes. So that's the internal process in order to differentiate the patterns that can be identified within the training sets. The score are comparable indicators from 0 to 1, so that's what we get back from the API. The score for custom classifiers are not comparable to the score written by the general classifier, which has classifier ID default. So if you get 0.5 in the general classifier, you may get 0.6 or 0.2 in a custom classifier. So they are not directly comparable. How to evaluate classifier accuracy? So you've done some training, you want to see whether it's accurate or not, and if it's not accurate, how to improve the accuracy by doing eventually some more training or modifying the training set and changing some of the pictures you have been using for the training. So here is a small kind of process where you assemble a set of labeled images that was not used in training the classifier. So we insist on the fact that for the validation of those machine learning models, you need to set aside images that you don't use in the training set in order to have valid testing. So because if you are using the images in the training set, they mean that there is a bias towards the recognition of what's in the testing image. So you put aside a certain number of labeled images, you split them into two sets, validation and testing. You run the validation set for the classifier. You pick a score threshold, and which optimizes the correctness metric you value. So such top 5 precision across all of the top 5 precision for all the classes across all of the images used for the validation set. And then you do from the test set, you select again a subset environment, classify it using your classifier and the score threshold that is meaningful to you, and you compute the probability of a correct classification. So you can repeat this environment with other subsets and compute the average percentage of correctness across all experiments. So the idea is that you not only need to create a model by training it, you need to validate that the results provided are okay, and to do that you need a testing set or validation set, and you need to get a kind of measure that will show you whether it improves or not. So presented in another way, the idea is, so you have on the bottom the line of activities. So you start, you take and tag images. So that's the first element. And you, as we said, you take images and you tag images according to the use case that you want to practice. So if you want to look for cracks in pipes, you take images where the crack is at least 1/3 of the image. You upload the images, and then you start this loop where you prepare and validate the training data. So here are the spots are representing various user roles. So the purple one is the SME end user, so who knows why we are doing this exercise, the developer for the user interface, and the data scientist for the models. So they train the model, and the developer and the data scientist are involved. The evaluation of the performance is more about more in the role of the data scientist. Same for adjust thresholds, and if the model is found correct, then you can deploy it. That's a developer role or developer and operations role, and then the application is in production, and the user feedback tells you whether you've got the right level of accuracy based upon what you're looking in the images that will be used by the user in their day-to-day operations. Okay, so just now to prepare for the labs, so tutorials 1 and 2 will be about the use of the visual recognition API. So to do that, and we'll start in a minute, you will have to connect to the cloud.ibm.com and create an instance of visual recognition, and you will find the instruction in the box that was mentioned before in the chat, so ibm.box.com/v/Watson computer vision 2 July, 2nd of July. So using the API. Then we will do a Watson Studio install. So it's another service, so it's just not very complex, but just you need to do it, and you will need to master the elements of creating a project within Watson Studio and connect this project to a resource, to an asset, which will be the visual recognition that you have created before. We'll do that for using the user interface for creating and using the general models, food, general, and explicit. So that's tutorial 3 and 4. Sorry, specifically for tutorial 3, we'll use the custom visual recognition classifier with the UI. So we will create a custom, we'll use images of dogs, so the different breeds of dogs in order to recognize more accurately not only that there is a dog in the picture, but there is a specific dog in the picture. And tutorial 4 will be about custom object detection. So the idea will be to create a collection of images. So it will have a specific PDF for that, with me for custom object detection PDF. And you will be able to upload files, to upload pictures, and you will customize those pictures in order to say, okay, the object I want to recognize in the picture is this. And for example, here you will train it to recognize skateboards. So you will highlight the skateboard with the square, and you will say to the system, this is a skateboard. So you will have to label it. So you will do the job of identifying the object and tagging the object. And then the model, you will train the model, and then you will see that there will be some capability to auto labeling, so that will help you doing this activity, which may be lengthy if you want to recognize many things. So user recognition, object detection, auto labeling features. After that, if we have time, we'll do the custom object detection. So the model you've created here deployed on Android, or use an already deployed, another created model and deploy it on Android. So either you have an Android phone or you have a simulated, an emulator phone. So you will be able to see what happens in this emulator. So it's kind of being able to analyze that in a picture there is something. Right? In the demonstration that is provided, recognizing Lego personage, Lego tiles, or Lego
characters.
Correct. Thank you. Thank you for coming to to assist me. And then the other one is tutorial number 6, which I already mentioned, which is rather lengthy because you need to install Xcode, and Xcode takes quite a long time to be installed into your machine. And even more, if you don't have a Mac machine, you need to create a kind of a virtual machine to install it. But you can do the custom visual recognition download onto an iPhone environment in order to do custom classification on iPhones, okay, or tablets or iPads, etc. Okay, so thank you very much for attending to this presentation. I am opening the mics now for end the show, and opening the mic for the questions, and then after that I will direct you to the instructions for the labs and the hands-on that I'm proposing to evaluate the tool Watson Visual Recognition.
So from now on, we have labs, yes? Or
yes. From now on, we have labs. Yes, sure. So I'm connecting to the box just to show the elements that you can get from the Watson Computer Vision Presentation Hands-on Labs. So the presentation is what we had up to now. And the hands-on labs folder, there is this 2020-06-28 Computer Vision Part 1 lab. So that's the main PDF describing giving the directions for the instructions for the labs. And you will see that you will need some images. So they can be accessed from the instructions as well. But in case you have some problems with downloading images, you can get them from the folders that are here. So one suggestion would be to download the complete folder to your environment. So that would be one way, or the other is to download on demand when you request it. So if we start the computer vision lab instructions, so we'll open it. Oops.
And Philippe, there is also a README file. Is this something they need to
Yes, this README file is for custom object detection. So it will be needed. It will be needed in a moment, and it will be referenced in the general environment. So the main element is the last file. So part 1 lab. And the other one, it will be referenced as tutorial number 4 in the lab. So you will not start with README, you will start with the part 1 lab, which is the most, say, the overarching document.
So we don't have any questions.
Excellent.
Yes.
So I will share as well the I will share the PDF. Okay. So the idea is to use visual recognition API first. So create some call commands and see the results. And then you will use for that the tutorials that are provided within the documentation of Watson visual recognition. So first you create an environment where you use a tutorial. So the tutorial will present all the steps and will guide you through the various steps to use the API.
So we can go ahead and start with the labs, yes?
Yes.
Okay.
So you go to the visual recognition page in the cloud catalog. Okay. So it gives you directly, if you are already recognized, if your ID is recognized, so you create, you can create a visual recognition service. There are three places where you can create a visual recognition environment. One is Dallas, another is Frankfurt, and the third is Seoul. So there's only one important thing is to create. To remember where you create the service, visual recognition, and when it will be time to create a Watson Studio instance, to create the Watson Studio instance in the same location. So it will be necessary to have an easy way to connect both services. So just remember to create both services either in Dallas or in Frankfurt, but above all to create them in the same location. So I will just connect to the cloud.ibm.com. So you go to the dashboard. You go to the dashboard, and then to the catalog. And within the catalog, you can get into the services. And in the services, the AI machine learning subcategory. And within this subcategory, you get visual recognition at the end here. So that's the catalog that was mentioned. So in the regions, you've got Dallas, Frankfurt, and Seoul. You can create only one light plan, so I will not be able to create another one. So there are some capabilities in the line plan that are enough to evaluate the service, but of course are not as extended as the other standard plan. So pre-trained model classification, general, food, and explicit, custom model classification, custom model training. You can get up to 2 custom models and 1 plan instance per IBM Cloud organization. And you can export your models to CoreML. And of course, if you go to the standard plan, you've got more capabilities, unlimited image classifications per month, unlimited custom models, unlimited free exports, and you've got the price here, which so tagging event, custom tagging event. So see the price is here is in dollar, but you can get, depending on the region you sign on, the price in the right currency. You can get as well, so there is the create, there is the about tab, which is interesting. The about tab gives you some information about the tool, and you already have that. But you have as well the links to the API docs as well as to the docs themselves. So the doc is the place where you can get the tutorial I'm referring to. So that's a way to close the loop. So once you have created the service, you can get here and you can get the tutorial to start using the APIs. So with the APIs, we'll use curl, but you could use eventually Postman or any other tool that you're familiar with.
Yeah, maybe we should just mention that on Windows, curl is not standard as far as I know, so it will be need to be installed on top. If you're on the Mac, it's okay because you have Unix, but otherwise, you need to install it.
Yes, yes.
And there is a source here, the curl axe, whatever.
Yes. So if you don't have the curl already installed, you will of course need to install it. And in Windows as well, you will need to modify the path so that you can curl from any location in your environment. You will see that in the curl commands, you will have to provide an API key as well as a URL. And the API key and the URL are elements that come from your service. So if I go back to my service, if I go back to my service, I will connect to my service. So when you have got your visual recognition service, you've got an API key as well as the URL. So of course, the URL is specific to the center. So here, EUD is a service created in Frankfurt, and there is no EUD, of course, if you create it in Dallas. And you've got the API as well as an instance name that constitute the full URL that you need to install into the curl command in order to get the right results. So here, an image is provided through a URL. So you see that you can analyze not only images in files, but as well access them through URLs. And you will see as well something that is important, the version. So the version here of the models, and 2018-03-19 is the latest version for the version 3 APIs. You'll see that when you are using the custom object detection. That's version 4, and there is another date for the version. So you should get from the command, you should get the following results. So images, classifiers, so all these JSON results that we saw on the demonstration. So all the details that are provided and the scores that are associated with that. So with some statistics at the end, the number of images processed and the custom class is 0 because at the moment we are using the general model. And if you want to use a different model, even if it's a built-in model, you will need to mention the classifier ID. So classifier ID is food, in case you want to analyze the food, an image against the food classifier. So you can either use here another image, or you can use the same one as before and see how it is. The results are different when you are using another classifier. So how to differentiate the results based upon the classifier you are using.